Okay, hello guys. How are you? Mr. Hewitson here with a quick run through the calculations from our prac the other day. We were forming resonance waves inside a closed air column. So by closed, what do we mean? Well, we had the measuring cylinder made of glass. We put water in the bottom. The water level makes a closed end, so sound waves can't penetrate through the water. They'll actually fix an end of the air inside the cylinder, and then the rest of the air between the water level and the top of the cylinder, that's a column of air. Okay, we had a look, and the diameter of that cylinder is about 5 centimeters. Well, the one I used was about 5 centimeters. So how do we work it? Well, I'm going to take you over to the whiteboard now so you can see how to do the calculations. So take a look with me now. I'll just take you over to share the whiteboard. Okay, so again, as you can see here, got a few bits and pieces. So the way it should have worked, if all had gone well, this would have been our column right here with this picture I'm showing you now. And so what we expected would have happened if it had gone smoothly is that as the tuning fork is struck, so you chose the frequency, so for example, middle C, 256 hertz, you strike the fork, you hold it above, sound waves at that exact frequency start bouncing down into the column of air, strikes the bottom of the water, and then it's got a column of air. What happens is they reflect back from the bottom, sorry, from the top of the water, bottom of the column, and they start to form a little standing wave like this, right? As you can see, I'm drawing the diagram on there now. So if we're lucky, they form a little wave. It's probably more like that. The first sound that comes down is just a simple sound wave, but what they do is it starts to reverberate inside that air column as it makes a second harmonic if the length here, the length is right. So once the length of right, so the length of the vibrating space is exactly right in centimeters, then it allows for this balanced second harmonic to form. The noise you hear at the start, of course, was just the tuning fork. It was actually very hard for us to make out the sound of the raised pitch. We were hoping to hear, if you had a C fork, hoping to hear a slightly higher pitch C, the next octave up in music terms, and that would be this one here, the F3. We know that in a closed cylinder, we form odd harmonics only. So you go from F1 to F3 to F5. So we were listening for this F3. It should have been a slightly louder sound and at a higher pitch of C. Still the music note C, but a higher pitch. I know that most of us had a hard time hearing it. The intensity is not always that loud. Once it starts resonating, it was probably there, might have been hard to detect. So I gave you an alternate method to be able to calculate this, right? So here's what you're going to do. What I'd like you to do is go to the hyperphysics resonance calculator. I'm going to show that to you right now. So I'll flick over to that. Here we go. So if you go to it online, the link is on Microsoft Teams. Here it is, air column resonance. Now you'll see there's 3 varieties of cylinder here, right? Open cylinder, closed cone. It's the middle one we want, closed cylinder, closed off with one end with water, and the other end of the cylinder is just an open glass tube with the air through it, of course, and the wave is even able to proceed slightly beyond the cylinder, which it actually does do. I'll talk about that a little later in the video. All right, so if you have a frequency like the one that I used in my group, we used a tuning fork with a G, a middle G, which has a frequency of 392 hertz. So what you do, you got to enter your data in over here under closed cylinder, right? See where my cursor is. So the frequency, I enter my fundamental frequency in there, and then I'll also enter up here a temperature value. It was pretty cold. We'll call it 20 degrees, and then click off somewhere. And it starts to fill the values, right? Now, I want to put in the fundamental frequency, which is F1. That's the tuning fork frequency. So I'm going to replace that value there. It's giving me the F1 there, right? So I put in the true F1 is 392 hertz, and then click away somewhere. And look, the values adjust, right? So for a fundamental G sound, boom, it goes vibrating down the air into the column. the calculator lets us know where I should have started hearing the second harmonic should have been when I had my column length at this exact length here. You should have actually had all three frequencies, but our ears can't hear all of them, right? But the one I had here of 392, I put it in. This is the value here that the column length should have been at. So I'll let you use the data from here, okay? From here. So use your calculator, close cylinder, enter in to 20 degrees and put in the frequency. If you had a C, it won't be 392. You got to put into F1 the frequency of your fork. So if it was middle C, it's 256. You can put that in. I put some sample data up on Teams as well for you. Okay, so we'll click out of there. What I found out that I'm going to memorize now is that the length of my air column was 21.9 centimeters or 0.219 meters. Okay, so I'll click back out of there and onto the calculations now. Right, so back to the whiteboard. We'll flick out to over there. Remember, when we're dealing with a wave like that, I've got my value over here for G tuning fork. I'll just mark that up so I can be sure I've got it straight. It's here in the closed cylinder. So these values in here, and I've got a column length right there, 0.219 meters. Okay, so what I'm going to do, I'll record that value. So record that as your measured value, even if you didn't hear it, you didn't hear that slightly more intense sound at the higher pitch. There it is. And then I'll move you back over to here. And to do your calculations, remember what we've got over here. I've got the mathematics here for closed column air. So these are the frequencies. I only get odd ones, F1, F3, and F5 with corresponding wavelengths, lambda 1, lambda 3, lambda 5. And over here, my equation that relates the frequency of the note, the sound, is equal to N times velocity divided by 4L. So I'm going to use my, just pretend I've got a fundamental one. So N becomes 1. Rearrange this equation. F to solve over here. So F is actually equal to, by rewrite the equation, multiply both sides by 4L. And I've got a nice, neat little equation here for the velocity. And that's what we're going to use, this equation, to find the velocity that the sound wave is traveling in air. That's the end game of this prac, to find the velocity of sound in air. So it's V is equal to 4 times the frequency times by the column length. All right, so it's over there. So let's put our values in. Now the equation is a little bit unusual. It's got a special add-on part at the end, which we'll show in just a second. All right, so here we go. Moving it up. Velocity of sound is what we're trying to find. F is the frequency of the tuning fork. In my case, it was, let's type that in, 392 hertz. My pen's being a bit dodgy. 392 hertz. The distance between the top of the water and the top of the cylinder, so the air column length, remember, was 0.219 meters. And the diameter of my cylinder was about 5 centimeters, so that's 0.05 meters. Now, look, I've got all my data. I can now substitute it in. Now, have a look at this unusual part of the equation up here. Look at this. I'm not multiplying 4F times L. I've got a special expression in brackets for L. Why is it this H plus 0.4 times D? Well, let's have a look at that over here. That's because this is actually what a standing wave looks like in a closed air column. It doesn't actually finish right here at the top. Doesn't go there like you'd expect it to. It actually forms all the way out here, just above the lip of the cylinder. So what I've got to do is have a maths correction to get the true length of the standing wave. And there's a mathematical consistency to it. The true length of the standing wave is the length you've got in centimeters, 0.219 meters, plus 0.4 multiplied by the diameter of my tube. So my diameter was 0.05. So now all I've got to do is substitute all those in. That's called a top correction. And you do it whenever you've got particularly closed cylinders. It's this little displacement effect, and you've got to account for that. All right, let's do our maths. Not too hard. I've got my F, right? So got my F and I've got my H or my L, and I can do a correction with 0.4 times the diameter, 0.05. All right, let's get our equation, right? So velocity is equal to 4 times 392 multiplied by the height, 0.219 plus 0.4 times the diameter, 0.05 meters. So I put all those in together, and if we just move that up a little bit, we can finish solving. Our value is there. I've got 1568 multiplied by, and this sum in here, my corrected length is not 219, it's actually just above 0.239 meters is the corrected standing wave length. And multiply all those out, I get a final calculation of 374.8, and that's the velocity, and that's meters per second. So that's actually the velocity of sound in air. So that's how you do it. Make sure you do it for your own experiment, right? You didn't use G, you used C, a lot of you did. Make sure that you go to the calculator and use the correct values for middle C, which are right here. I'll put them here in the video for you as well. It's going to be these values here for C. So I'll just mark those out for you. So if you've got middle C with a frequency of 256 right there, then your length is going to be right here. It's actually 3.335 meters. Don't forget, it'll have to go in for a calculation. The column length for the wave is slightly longer than that, but your equation will make up for that. And let's see how close you get. Notice that the standard velocity in air is meant to be 343.7 when we're at 20 degrees C. I have actually come out with my value being slightly higher than that, and I guess we can account for that with experimental error and probably the fact that maybe my temperature estimate is not exactly the same. So the value I'm comparing with over there should have been 343, 374. It's a little high, but it's still pretty close. So we'll regard that as useful. All right, get to it. Make sure you complete those values on your worksheet. And I think that'll do for now. Okay, toodaloo.